Okay, welcome everyone to today's webinar on materials in extreme conditions. This webinar is sponsored by CDAC here at UIC, as well as the Center for Matter Under Extreme Conditions at UCSD, as you can see. It's a real pleasure to introduce our close colleague and longtime friend, John Eggert, to give this webinar. John is a physicist who specializes in extreme conditions with really quite enormous breadth, having made many contributions in both static and dynamic compression methods and discoveries over a wide range of extreme environments. These include a variety of laser-driven dynamic compression diagnostics, dynamic X-ray diffraction, and X-ray free electron laser methods and results, which he'll tell us about today. Hugonio stress density measurements, ramp compression studies, studies of compressible fluids, melting, and deviant historic stress measurements. He's also contributed to the indirect drive inertial fusion efforts at Livermore. John has a BS in physics from Montana State University and a PhD in physics from Harvard, where he started out with diamond anvil cell studies of pressure-induced insulator metal transitions in xenon and hydrogen. And it was actually during that time, I think it was in 1988, that we met at a winter school in the Alps, where we had a memorable time, not only for the great science that was discussed there, but because of a terrifying ski run we took down a glacier on the side of Mount Blanc, which he led. After this time and his graduate studies at Harvard, he moved to a postdoc position at the Institute of Physics Beijing and then joined our group at Carnegie after that, where he produced some of the most impressive results of our group at that time, and we had a great deal of fun. He was an assistant professor at Pomona and Colorado School of Mines, spent time at CEA Paris before joining the laser shock equation of state group at Livermore, which marked his shift to dynamic compression. He was a group leader in the dynamic materials properties group from 2015 to 2020 and has been chief scientist in the HED Center since 2020. John also recently joined CDAC as a member of our scientific advisory committee. So John is not only fearless on skis, he's also fearless in pioneering new techniques and taking on grand scientific challenges. And I think he'll tell us about some of that today. So over to you, John.
All right. Thanks, Russ. Thanks for those kind words. And yeah, my memories of postdoc at Geophysical Lab, those were great times. Learned a lot of science and a lot of really fun experiments. So that was a great introduction to the world of physics. So today I'm going to be talking about, see if I can figure out how to move forward, about X-ray diffraction using laser-driven dynamic compression. And I don't think I need to say much about this slide to people here, but most of the matter in our solar system does exist at extreme pressures and temperatures. We like to talk about it as HED, high energy density, which if you remember back to your undergraduate years, that has the same units as pressure. And so it's essentially an easy way to say high pressure, except when you talk about high energy density, you can also talk about putting thermal energy into your system. And so it's a way to kind of combine all of the physics that extreme physics that places like Livermore are really interested in. So we can talk about plasma physics and high pressure physics all in the same sort of groups. And so we generally say HED. And with laser compression at the NIF and such, we can actually make real measurements of things of materials up to very high pressures. We have measured up to 50 megabars in diamond, which is getting close to the core of Jupiter, and above the core of Saturn, which is pretty neat. We can do X-ray diffraction exceeding the pressures at the cores of Uranus and Saturn, or Uranus and Neptune, and so it's pretty exciting to be able to actually look at what's inside of planets, and especially large exoplanets where it's very difficult to do seismology or something to try to explore what the centers of those planets look like. And so doing laboratory experiments, both in diamond cells and in dynamic compression, is really important for planetary science in general. As Russ said, I started out in static compression, and so I think it's really interesting to compare the two, static and dynamic. Can you see my cursor? I don't know if I'm not exactly sure how to turn this into an arrow.
Yes.
Okay. So static compression experiments impose boundary value conditions, and so you're essentially putting a large force onto a container, and that raises the pressure, but it'll stay there for a long time as long as you keep those boundary values on. Dynamic compression impose initial value conditions, and so we're essentially driving either with a gas gun and a flyer plate, or with a laser ablating a material at time equals 0. We put a very large pressure on our material, but then it has to transit through the sample. So if you think about that, the types of partial differential equations that describe those, parabolic differential equations like the heat diffusion equation, are governed by boundary values, as are elliptic PDEs like Laplace's equation. So those are generally the types of equations that you're solving in static compression. Dynamic compression, the PDEs are hyperbolic, and hyperbolic PDEs support waves. Parabolic and elliptic do not. And so the response is not instantaneous. We have to wait for these waves to travel through our sample, and everything happens at a finite propagation speed. So measuring things like what happens as a function of time is critical to us. And nothing stays for very long in our experiments. Here's a very simple PT rho equation of state. This is of aluminum, I believe, and John Paul Davis at Sandia made this a number of years ago, but I think it's a really nice way to talk about things. So if you were in a diamond cell, say at room temperature, you would be essentially following an isotherm up this path, and you would get to the same temperature, so you're just compressing. You could also do a dynamic experiment where you're taking advantage of the fact that you can send a shock wave moving through your sample. The locus of points in this space for a shock wave, single shock wave, is the Hugonio, and that gets very hot very rapidly. Well, rapidly in the sense of megabar pressures, and so this is where the HED designation comes about, because you continue to put more and more energy into the material, but you're getting so hot that you can't compress it anymore. So dynamically, if you want to compress to high densities, you need to follow something that's closer to the isentrope. And in fact, if you ramp compress something and it has no strength or other dissipative mechanisms, you can essentially follow an isentrope. And so in a liquid, for example, following an isentrope is relatively easy. In a solid, you've got strength, and so you get plastic work heating, and you're a little bit higher pressure. But using dynamic compression, if we can use both a shock and then a ramp, we can actually access this entire temperature, density, pressure region between the Hugonio and the isentrope. We can never get below the isentrope because there's not enough time to pull energy out of the system. We use high energy lasers. We use what's called an ablation process where you shine a high energy laser on a material, and you turn that material, the surface of that material, into plasma, which then jets out back toward the laser and forms essentially a jet. So it's essentially the rocket equation. And as you know, for driving a spaceship, you'd prefer to have low Z exhaust that you throw out. It's more efficient. And so we tend to use low Z materials as our ablators. The other good thing about that is that when you shine a laser on and form this plasma, you get a lot of X-rays coming out. And lower Z materials have lower energy X-rays, which are easier to block, easier to filter out, and so you get less preheat in your sample. And the size of the lasers are quite large. NIF is a 2 megajoule laser, and we generally use between 10 and maybe 300 or 400 kilojoules at NIF. At Omega, generally up to about 20 kilojoules, and at the XFELs, we generally, right now, our biggest lasers at XFELs is at MEC. It matters in extreme conditions at LCLS at Stanford, and that's 100 joules. And so I'll go a little bit more into that in a bit. So a couple of things to remember about dynamic compression experiments. We're going to assume, so these four are our primary assumptions, and they're all very good assumptions, that we're in local thermal equilibrium. That means that we're not necessarily in equilibrium as far as which phase we're in, but as far as the pressure, temperature, density, we're assuming that we're in thermal equilibrium, even right after a shock moves through our material, which basically means that the electrons and the protons are in thermal equilibrium with each other. The geometry is one-dimensional, and it can be planar, cylindrical, or spherical dimensions, but it's one-dimensional. And for everything I'm going to talk about here, we're in a planar dimension, so we have a flat shock moving through a flat material. The strain for all of these uniaxial or one-dimensional compressions, strain is uniaxial, which means that there's not time for the atoms to actually move in the transverse direction. So all of the strain is going into compression in one dimension. It also doesn't mean that the lattice constants are uniaxial. So we're not uniaxially compressing crystal structures, but because we get plastic deformation that relaxes and so that the atomic strain within, the lattice strain is not uniaxial, but the global strain is, and that's called inertial confinement. And the conservation laws of mass, momentum, and energy are obeyed. So you can write those in several ways. The conservation laws, you can write them in the differential form, which is shown here, hydrodynamic equations. You can integrate them and show them here, and you can take a difference equation. And I've written them so that you can see the connection in all of those representations. The difference equations are the equations for the Rankine-Hugoniot equations. So they describe what happens in a single shock into a material. The integral equations are what you have to solve if you're going to do a ramp compression experiment. And you notice here that there's 5 variables in the Rankine-Hugoniot equations, 5 variables in all of them. There's the pressure, the density, the internal energy, and in the shock compression, the shock velocity. In ramp compression, it's the sound velocity and the particle velocity, the speed at which the particles are moving after the shock or the ramp moves through. There's no mention of temperature. And so that's one of the big issues with dynamic experiments, is that it's extremely difficult to measure temperature. And I was going to talk a little bit about that, but I determined I didn't have enough time. So I'm not going to talk about methods of measuring temperatures, but we are developing temperatures beyond thermal emission, using X-rays and different techniques to try to get to the temperature, but all of those techniques are relatively new, and a lot of them require XFEL sources. We use a velocity interferometer system for any reflector called a visor to measure these velocities, because two important of these in red are the shock velocity and the particle velocity, which we can measure using a visor, which is essentially an interferometer that we run a laser, we bounce a laser off of our sample, we look at the reflected light of the laser, and we have a non-equal interferometer here, and we tune it so that we see fringes. As the frequency of the reflected light changes due to the Doppler shift, we see a change in the phase of the light transmitted through this interferometer, and that shows up as motion of these fringes. And so the the amount that these fringes shift is proportional to the velocity that you're measuring. So in a couple of these slides, you'll see images that look kind of like this, and that's the way that we know what pressure we got to, because we can use known equations of state of our materials and the velocities that we observe to determine what pressure we're at. So whenever I drive around California, I love looking at these, especially in the wintertime. I like looking at the vineyards, because you can kind of pretend that you're a crystallographer as you drive along. And one time I saw this field and it was so pretty, I decided to stop and take photographs of it. And then I decided to try to simulate it on my computer, which I did. And it turns out that you actually can determine how the vintners decided to plot their crops. And this one ended up being a square lattice with about a 30-degree rotation from the road. And so it's kind of fun I think it's fun to drive around and look at these things. And from this crystallography and from the diffraction that I'm going to talk about, we can measure the equation of state, the stress density. We can measure the structure of the phases. We can measure transmissions between different structures, and we can look at how rapidly these transitions happen, and we can measure many properties of these transitions, and we can measure plasticity and defects in the materials. So I'll talk about all of those. So to go back, the first shock compression the first shock compression of diffraction was done amazingly early in 1950, which is not very different than the first time that diffraction was done in static compression. But not much was done with it, partly because the data is not very good. And it was, 17 years until Quentin Johnson at Livermore demonstrated that he could do nanosecond resolved diffraction. The first shock experiments were microsecond X-ray sources. Johnson developed a nanosecond source and measured much more rapidly. He demonstrated that you could measure a phase transition by diffraction in a shock compression in 1972. But again, these experiments were really hard to do, and so not much happened until 1986, when Justin Wark, who's still a professor at Oxford, still doing similar experiments, again in Rutherford lab and at Janus at Livermore, did a divergent beam single crystal diffraction using laser heated single crystals, and this shows some of his data. And so this one was, I believe, on germanium or silicon samples. And that the concept of this is that he used a point source. So I'll go into how he made the point source in a second. But the point source, and then it diverges rapidly. And this distance from your point source to the sample is very short, a couple of millimeters. And so you get the the angle of incidence on your sample is different for every location in your sample. And if you assume that you've got a planar shock, planar uniaxial shock moving through your sample, the mapping the position of the reflections uh, allows you to look at different diffraction angles. And so it's kind of a neat idea. It was developed more by people at Livermore and Justin. Um, and in 2005, this is when I came on the scene here at Livermore. Dan Kalantar wrote this very good paper looking at the iron phase transition, the alpha epsilon transition in iron, and we were able to see it at the Omega facility and Janus. And the technique that Dan used is just a little bit different than what Justin had. Here we had an iron foil that we put about 2 millimeters away from our sample. We shined other lasers on the back of the sample, so we drove a shock through the sample. We focused a backlighter beam, kilojoule backlighter beam that was focused tightly, 300 microns or so, which basically makes this a very hot plasma, which then emits. You strip all of the electrons off of the iron foil until you've got basically 2 electrons left, and then you look at the K alpha, or it's a helium alpha, but it's the excitations when you excite and cause fluorescence of those helium iron. It's a helium atom with an iron nucleus, and that emits a relatively monochromatic, bright X-ray source. And then, but it goes in all directions. And so that gives this diverging beam, and then you put image plates very close to your sample as well. And as a function of angle, you can see the single crystal diffraction. And this shows the data that we obtained. You can see there's a lot of lines here which we identified and were able to analyze what they looked like, and we were able to see as a function of pressure how the alpha epsilon transition in iron occurs. So after we did that work, it became very clear. I was highly suspicious that we would be able to get to megabar pressures with single crystals. And so I really wanted to develop a technique for getting samples that were powder samples to compress. And I also wanted to ramp compress them so that we wouldn't shock melt everything at a megabar or two. And so what we came up with was a low Z ablator, like I already talked about, the rocket effect to drive a wave through our sample. We can change the intensity of the laser over time, so we can make it so that the laser starts off very low intensity and then increases in intensity. So the low pressure waves will travel first through the sample. They'll get to the sample here, and then we have a window on the other side. And as you get into the sample, you get reverberations, and so you're going to have the sample is going to rise in pressure with the window and with the ablator, and essentially you can see that the pressure wave moving through your sample gradually increases the pressure within the sample. And so when you get to sort of this 2 wave, you can have a steady ramp compression wave sitting in your sandwich target for, and we can generate that for on the order of 5 nanoseconds. So this is the technique that we use, and then we can measure the velocity of either the interface or the free surface velocity to get the pressure that we're at. So this is more what we did. We used then we used again the helium alpha radiation that was used in Dan Kalantar's, where we have different angles, but we wanted to collimate it now. So we've got monochromatic light, relatively monochromatic light, but it's divergent. And so we collimated it with a high Z pinhole. We put our sample on top of our pinhole. And so we've got light from our backlighter, from our helium alpha source that's coming in at many different angles, but only a select set of angles goes through this collimating pinhole. And then we built image plates that we stacked all the way around it. And this shows an experiment where here we've got a space-time, space in the vertical direction, time in the horizontal, that how we calculated that the the stress in the, we used a diamond ablator and a diamond window on this experiment, iron in the center, and you can see how the stress of the material changed with time. And then we time the second laser that makes our X-rays so that we have this constant maximum stress. And then we can confirm that we did that correctly by measuring the Visar data off the free surface of the diamond. And this is the timing of the laser drive and the timing of the X-ray source. So we first used this technique in 2008 at Janus at Livermore. It was a lot of fun. It turned out on our third shot, we actually got, this is the data that we got. This black region is what we saw in the first two shots, because we used a very simple image plate holder, and we found that we were getting a lot of X-rays through a centimeter of aluminum, which surprised us because the helium alpha radiation from iron is at about 8.3 kilovolts, which should get absorbed by a factor of 1,000,000 or so through a centimeter of aluminum. But we were getting very dark signal. And it turned out the reason for that is because when you make these X-rays, you get a lot of bremsstrahlung. So you get a lot of hot electrons that come out of this X-ray source and fly around. They can hit the sample. They can hit the backlighter itself. They can hit the pinhole. They basically bathe everything in high energy X-rays. And we're actually getting, I looked at the data a year ago from the first two shots. We can actually see that the absorption in tantalum, and we can get a kind of an estimate that we're having 60 or 70 keV X-rays come out, which do get transmitted through the aluminum. And so in this experiment, we put a piece of lead in front of our sample, and then we got this diffraction. And we very rapidly, by January of 2009, so in just 3 months, we built what we call the Pixar DIP, the powder X-ray diffraction image plate system at Omega, where we just built a box out of tantalum this time, where we put image plates on the inside of it. We have this pinhole with the sample sitting on it here. And this shows kind of the diffraction and how we get it. So you can see we get a direct through down on the bottom here, and we can see diffraction on the three other image plates. In 2013, we transferred to NIF with a target diffraction in situ diagnostic, which we call the TARDIS, which has had a lot of NIF shots, 205 NIF shots, which is quite a bit considering that NIF does between 250 and 350 shots per year. So over 12 years, we've had a lot of shots. 70 of them have been discovery science shots that are proposed by academics to do basic science. 125 have been from programmatic shots at the lab, and there have been 10 ignition shots that were done trying to understand the ablators for ICF. And this target is flat because of the way that they align beams on NIF. So I'm going to show a couple of results from this work. So the first is an experiment that was done by Rick Krause. He wanted to measure melting in tantalum, which he did. And here you see what the data looked like. And this is the diffract, the 110 of BCC tantalum, and it shifts up with pressure, and then it gets very weak and it gets broad. And this kind of shows the that peak kind of translated, so you can see that At about 264 GPa, you start to broaden this solid line, and these three images in black are shown as these three in black here, where the density doesn't change very much, and you see that the intensity drops and you start to broaden it. And so we interpreted that that was the melting of the transition, which corresponds great to what was measured in gas guns. So that was exciting. We measured superionic water, also using Pixar-Dip. This was led by Marius Millot. And same experiments. You can see the data here. This is the water ice diffraction. When we tried to dewarp these images and plot versus 2 theta, this is the data, and you can see this water line is here, and it's shifting as it should for a BCC phase. And I have a typo here. This should say face-centered cubic, FCC in the red, and it shifts to lower 2 theta, which is inconsistent with continuing to compress it, and that's because of the phase transition. And so we saw this change from the BCC phase in blue to the FCC phase in red on the phase diagram, and the FCC phase was what theorists predict should be superionic water. Melt curves of iron under Earth core conditions. This was also Rick Krauss, did an experiment similar to what he did in tantalum, but now at NIF, where we went to about 500 GPa and also about a terapascal. And we measured the transition from the HCP phase to, we had one shot where we saw HCP plus a liquid, and then 3 shots where we saw complete liquid. And so we were able to extend the melt line of iron up to about a terapascal. This one shows in entropy pressure space, and this one in temperature pressure space. We also wanted to look for the BC8 phase of carbon, which carbon is a tetragonal crystal structure. So you've got perfect sp3 bonding in diamond, which makes it very strong and very stiff. The BC8 phase is not nearly as symmetric, but it also has very nearly tetragonal bonding also. And this transition should happen, all the theorists predicted should happen at about a terapascal, about 10 megabars. We compressed up to 20 megabars and we still saw diamond. So that was frustrating. I really wanted to see this, but we were unsuccessful back in 2018, 2019. And Amy Lizicki published, the first author on this paper, in 2021. Currently we have more discovery science campaigns where we're trying different ways to get up to this phase, and we're optimistic that we will see this phase within the next few years. So crossing our fingers. We've also developed a time-resolved diffraction on NIF. So NIF can drive, we've done drives up to 90 nanoseconds using the NIF by stacking pulses. The NIF lasers have 30 nanosecond drives. The fiddle diagnostic uses Icarus detectors, which are HCMOS detectors that are built by Sandia National Lab. We put 8 of them. Well, so far there's only 5 of them in a target. The reason that this container is so big is because there's a lot of electronics, and these can sample every 2 nanoseconds. So they turn on for 2 nanoseconds, to turn off for 2 nanoseconds, and we can measure time resolved for 4 frames of diffraction. This shows an observation. We ramp compressed iron, and we saw the HCP to BCC transition in iron as it was being compressed. And so here Kara has labeled the orange diffraction peaks are the HCP peaks, and the blue ones are BCC. So we go from at time equals 0, we go from a complete HCP structure to 12 nanoseconds later, we can see a complete BCC structure, and we can see the transition between it. And we're now up upgrading this to a new diagnostic, which we're going to get all eight detectors on it, and we're optimistic that we've cut the background down substantially, that we'll be able to get much better data in a year or so. So these are all the large laser diffraction patterns. I'm not going to go through them. I've shown this one in 2003. I've shown Pixar dip. There's a related BBXRD to measure Lowry diffraction. This is the TARDIS. There's a similar diagnostic at Orion. There's a diagnostic that Andy Krieger tried to develop to do radial diffraction at Omega. This is the first time resolved diffraction that was developed by Robin Benedetti. Fiddle, which is now being led by Cara Vernari, and that's shown here that I showed data from just now. Lully in Paris has a diagnostic that looks a lot like the Pixar dip. And then there's even a diagnostic that looks almost identical to TARDIS that's being used at Shenzhou 3 laser in China. And I mean, it's kind of nice to see that they're using our design, and they were actually very kind in their paper, and they acknowledge that it's basically an exact copy of what we're shooting at NIF. But they're taking really nice data now in China as well. This is the relative sizes of the laser spots. So NIF has a very large spot that we use to do the diffraction. At Omega, it's substantially smaller, but the energy of the laser is smaller. And Janus at Livermore is smaller still and smaller energy. These are DCS is a synchrotron in Chicago. The APS synchrotron, and MEC is the LCLS XFEL in Stanford. And those lasers are much smaller, so we focus them down a lot. And what's nice about that is it's really the intensity that that gives you the pressure, the power that you put, well, the intensity that you put onto your sample. And so by focusing the laser down, you can use much smaller lasers and still get to high pressures. And so there's a number of small lasers that are built. This MEC matter extreme conditions at LCLS in Stanford, DCS at APS in Chicago, SACLA is an XFEL in Japan. The dipole laser at the European XFEL in Hamburg, Germany. And then this is the ESRF synchrotron in Grenoble currently has this laser, but unfortunately it seems like that's probably going to shut down in the next year or so. But these are all less than 100 joules. But they can still give really nice data up to about 1 or 2 megabars. And so I'm going to go quickly through a couple of things that we've done. This is in zirconium. So we use single crystal zirconium, C oriented. And so zirconium starts off in the HCP phase, and then it transitions to an omega phase. And we were surprised so we start with a single crystal where we can't see any diffraction. So we purposely orient our targets so that we don't see any single crystal diffraction. When we shoot it, we do see some undriven alpha diffraction. Or no, this is not undriven. This is driven alpha diffraction. And it splits into some very sharp spots, but not in the same orientation as we started with, and they're not all the same orientation. So we get several different orientations, but we can actually see what the texture of the sample is, and it turns out that it's essentially a twinning process where we get kind of we compress the material and it twins. And then the omega phase, we started to see diffraction from that. It's also highly textured, but we only saw 1 peak, and we should have seen 5 or 6 peaks out here in 2 theta. It wasn't until Suransh Singh, who was the first author on this paper, interpreted, he was able to simulate the pole figures of known orientation correlation functions. So basically, if you move the atoms in a specific way, you'll go from one orientation of the alpha phase to another orientation of the omega phase. And it turned out that when he calculated um, the pole figures, that only this line was the one that would allow diffraction. All the other ones were at the wrong angles for the energy of the X-rays that we were using. And so we were able to determine what the orientational relationships between the initial phase and the final phase were. And what was really surprising, as we went up in pressure, we saw three different variants of the omega phase that involve different orientational relationships, different ways that the atoms are moving around for the same orientation. And as we move through it, the amount of signal that we got in each variant was different. And so we initially saw this variant 3 and variant 1, and then the variant 1 remained constant, the variant 3 started to fall off, and variant 2 started to overtake. So it was really interesting because in previous experiments, people weren't able to tell what the preferred mechanism was from dynamic experiments. But we were able to show that it's not just a single transition. This was another experiment led by Chris Warenberg that was really neat. We used purposely textured in a fiber textured tantalum, and because of that, we could see just kind of spots. He was able to kind of say why we see these spots based on the fiber texture, and then when we shock compressed it, we got twinning, and we got rotation. And so you can see new peaks out here that are different from just compression, and you can see kind of a peak splitting due to the rotation of the lattice. And this shows basically the twin fraction on top and the rotation angle underneath as a function of pressure, which was kind of neat for how do dislocations in twinning mediate the plasticity. So diffraction is great, but what can we do if we have something that's not a nice vintner who planted everything? This is an image of a wild grapes. And when I was still doing static experiments, when I was on leave at the CEA in Paris, we developed a method to analyze high pressure liquid diffraction. And so I'm going to go through, there's a lot of equations in the next two slides, so I'm going to go through it really quickly. So the intensity that you measure in your diffraction is built of a lot of corrections, but it's basically this coherent scattering that we care about. The incoherent is things like Compton scattering, and you've also got background. So all of the underlined things are corrections that you have to apply to the data to start off with. And then once you can pull out the coherent scattering, then you've got the atomic form factor, you've got the density, and you've got basically a Fourier transform here in order to get the coherent scattering. And this G of R is the radial distribution function. And so this is what we would really like to get, kind of the structure of the liquid. So you can Fourier transform this incoherent scattering, and you can write it in terms of the coherent scattering divided by the form factor forms the structure factor. You can Fourier transform the structure factor to get the radial distribution function, and that's kind of the standard way that people analyze liquid data. The problem is that the form factor, the density, and the scale factor of the background are all unknowns in a diamond cell or in a dynamic compression experiment, because you don't know, in a diamond cell, your background is going to change because your gasket changes shape. In a dynamic experiment, the ablation plasma is going to be different in different densities on each shot. The density is obviously changing. That's not known a priori. And the form factor, even the relationship or the shape of the atoms is going to change with compression. And so all three of these change. And so many people that do liquid diffraction say, well, it's impossible to do in at high pressure. But when I was at the CEA, we came up with a way to do it. So we start off with this function, and we recognize that below a critical distance, G of R has to be equal to 0. And if G of R is equal to 0, then this representation of the distribution function f of R is essentially just proportional to the negative density times R. And so we define a delta f of R, and we say that we're going to define delta f of R as f of R minus the 4 pi r rho for R less than this critical distance. Then we can Fourier transform, so we correct this Fourier transform, and then we Fourier transform it back to get another iteration of the structure factor. And then we do this again. So then we take this new structure factor, we Fourier transform it to get the new f of R, and we repeat this. And the convergence is very rapid, 2 or 3, and I'll have an example of that in a slide. And then we repeat that with different values of S, rho, and the critical distance, and we try to minimize this delta f of R. And so basically, we're trying to get as close as possible in this f of R to having, or we're trying to basically get G of R to have a radius where it goes to 0. And it turns out that when you do this, you also optimize the atomic form factor. And so I did this in 2002 following a paper that was written in 1965. This paper, people don't believe it in the liquid community because they say that it tweaks the values that you should be using the density and not have to change values. Kaplow didn't actually change the values. He just did this first iteration. This shows from my original paper what happens as you do this correction on that iteration. So the first time you get f of R, you get these big variations in the low R. When you do the analysis, you get it so that it rapidly converges to this sort of straight line at the low pressures. And then you can look and try to get this line as straight as possible by optimizing the background subtraction and the density. So this has been, now there's 3 programs that actually do this. So my program I can't run anymore, but there's Glacier by Clemens Pressure, who does it, Liquid Diffract by this group, and Morpheus that also that does it. So there's 3 really nice programs that automatically do this minimization. This shows tin data that we took at the European XFEL, and the analysis that we did. This is the intensity, this is S of Q, and this is G of R that we obtained from that analysis. We've also done it at MEC, at the LCLS at Stanford, at DCS at the Advanced Photon Source, and this shows data from all of them, including a QMD simulation. And it shows that basically we get the same G of R and the same S of Q when we do this analysis, and the densities are shown here at kind of comparable pressures. I plotted comparing to gas gun Hugonio that's been measured, and the experimental data are the blue one from the European XFEL, the red one from LCLS in Stanford, and the orange one from APS DCS, and they all agree very well with the previous gas gun data. So, and this has been shown for probably 5 different materials in dynamic compression and probably 15 different materials in diamond cells. So I believe that this actually does give the right density. And now our challenge is trying to convince the global community that what we're doing is correct. So an approach to that, we looked at a metallic glass at the European XFEL. The data is the pink one here. And we also measured it, David Keane measured it at the diamond synchrotron in England. and he measured it out to, I think, 35 inverse angstroms. And the black line is what he got. And so our analysis gives the structure factor very good agreement. And G of R is also in very good agreement. And this broadening and weakening of the first sharp diffraction line is essentially because of the Q cutoff that we're forced to do. So we've purchased big detectors that we're installing at LCLS. We've done one run with them, and we're going to do another one in February. And this shows the quality of the data that we got from it, which is very good. And we designed these so that they can be placed anywhere within the chamber. And so we can put them in this configuration, which will get us out to 20 inverse angstroms at 25 keV, and we can operate at 18 keV now at LCLS, which should get us out to 16 inverse angstroms. Typo there. It also gives us much better coverage than the detectors for the data that I was showing before. So we get better azimuthal coverage. So we'll be able to do all of those experiments much better, and we get enormously better 2 theta coverage. So we're excited about that. Now I'm going to go to a couple of, I'm kind of running out of time, but this is dark field X-ray microscopy, DFXM, that Leora Dresselhaus-Murray developed when she was at Livermore. And this shows kind of a neat experiment in aluminum at close to the melt temperature, static aluminum. And you can see things moving around here. See if I can get it to start again. But you can see these sort of defects. These end up that they're dislocations. So single dislocations that you can image in the dark field X-ray microscopy. And they're moving around and breathing and doing all sorts of weird things. One of the things it does as we went a little bit higher temperature, you can see these dislocations moving, and they form this this array, which you can see starting to form out here, or I think it's this one. But you can see a dislocation inserting itself into a linear lattice of dislocations, which I think is really neat. And we would love to be able to do this dynamically. So we did one experiment at LCLF where we used a short pulse laser, drove diamond, and you can see 2 waves. You can see the elastic wave moving or the longitudinal wave moving very rapidly through this crystal. That's it returning. You can see this is the elastic wave, this is the transverse wave. And you can see that there's this pulse that goes through due to kind of this density packet moving through the sample. While we were doing this, we also noticed that we could look at the in the bright field, we could see a topography measurement that actually gives information about the defects within the density defects within the crystal. So we did an experiment like that also, and this one was driven. So at ambient conditions, we saw these orange peaks of our sample, and on the kind of the bright regions is because of the polishing defects in the single crystal diamond. And when we drove it up to roughly the elastic limit, we saw very, very big diffraction. So we no longer saw the single crystal. So we're trying to figure out what it is that's causing this. I think that it's that we're forming a lot of defects even within within the elastic regime, which is exciting to be able to look at those sorts of things. So I've got a huge list of thank yous. All right, so that's it. And we just ran last November. We ran a community priority access beam time at in Hamburg that had 110 scientists total that were doing experiments, 40 projects, 34 institutions, 12 countries, which was a lot of fun, and we're starting to get really nice analysis done from that time a year ago. All right, that's it. Thank you.
Thanks, John, for a terrific talk, a real tour de force. I remember all the naysayers about doing liquid diffraction measurements,
That's right.
dynamic compression, and it's interesting you're still finding naysayers out there. But anyway,
We still have a real I mean, we went through in what was it, geophysical letters. We had a review that lasted over a year long, and he eventually didn't get accepted because we couldn't convince them that this technique was legitimate.
Yeah.
So
Well, it's also great that you brought in the early diamond cell work and how useful that's been in this development. So,
yeah.
sure, there are questions and comments. Just unmute yourself, raise your hand, put your comment or question in chat.
Hey, John. Lovely talk. Just a quick question regarding the BC8
Yeah.
structure. So you mentioned that you're currently exploring because the theorized thing at 1 terapascal didn't work out, and it didn't even work out at 20. What sort of discovery stuff were you mentioning? Being able to extend that even further. That seems like
So
it'd be pretty difficult.
if I can get back to there, beyond that, this one. Um, so what we're doing is that we've done MD simulations with Ivan Olenek at University of South Florida, who's doing these huge billion atom simulations. And in his simulations, what he finds, Sandro Scandolo back in the 90s predicted that it would be very difficult to do this because on average you have to break over 3 bonds in order to, so it's a highly reconstructive transition. And so it takes a lot of energy to go through this transition. What Ivan found was that when he gets this transition to go, it it actually melts before it freezes. And if you kind of extend the melt line, you can believe, and simulations agree that the diamond should melt at a lower temperature than BC8 should melt. And so what we've been doing with Yvonne is triple shock experiments where we try to get into this range at about 20 megabars into the range where the diamond should melt, and it should be very easy to melt the diamond, and then the liquid will rapidly refreeze. In the simulations, it refreezes within picoseconds. And so that's what we've been doing with Yvonne. And then there's also with Dominique Krauss at University of Rostock in Germany. He's been doing a lot of experiments on X-FELs where he um, takes plastics, like just plastic CH, and double shocks it and forms diamond from that. And so our hope is that he's been kind of mapping out the phase diagram, showing that you need high temperatures to form the diamond. So we're going to triple shock that experiment also. We're going to try to get to 2 shocks where we don't form diamond, and then in the final shock to form diamond, have the hydrogen diffuse out, but start with an amorphous carbon material that will, instead of, will be at high enough pressure that we don't form diamond, we form the BC8. So those experiments should be starting next year, I think in March. So we're excited that one of those will work, or hopefully both of them will work. And it should be exciting because that should be a metastable state also. So it's possible that we could come up with a way to recover this phase, and you can kind of see there's probably a lot fewer cleavage planes. So BC8 may be, it's predicted to be just as strong as diamond, but much, or just as hard as diamond, but much stronger in tension.
Great. Thank you very much. Yeah.
More questions, comments?
I have a question if there's time.
Yes, go ahead. Oh, Malcolm.
It's
Hello.
Malcolm Guthrie. That was a really nice talk. I appreciate you taking the time to show some of the details of the shock compression without going overboard on the maths and keeping it intelligible. Yeah, I just had a question. I was staring at the current slide and I saw the data you have on the diamond as a function of pressure, and you have the real
Yep.
data there, and there's kind of bluish purple colored features on the graph, which I guess
Yep.
are showing what you would expect from the calculated structure, so you can compare that with the data.
That's right. Yep.
And I'm seeing that the 220 and the 311 they're visible, but very weak relative to what you expect. Is that
Absolutely.
just
Yep.
a massive thermal motion effect?
Well, it is thermal motion effect. So that's one of the techniques we're trying to use to measure temperature with the Debye-Waller factor. It's hard to do that because there's a lot of other things that weaken um, high angle diffraction lines besides temperature. Um, the biggest problem, though, is that when you go to high pressure, since you're ablating, you're using your laser to ablate your sample, which then is a plasma that can fluoresce, and you get and then also the lasers interacting with the plasma, which then makes more hot electrons and X-rays. And so I said we were getting a lot of X-rays, and we know that we're getting X-rays in excess of 100 keV and everything else. And it turns out that the ablation plasma is emitting so many X-rays that our background is extremely high. And we've tried to filter off the flat, the smooth background off of this, but our signal to noise or signal to background for this 111 peak at the highest pressures, which is this one shown here, is about 1 to 200. So signal to noise is not that low because we can subtract off a smooth background off of a lot of it, but it just gets so hard to pull anything out because you've got so much background from the X-ray diffraction, which makes it really exciting because we won't have the same problem with synchrotron and XFEL experiments because we can do much better filtering of the X-rays, and we have much narrower lines, and we have more intensity. So we think that when we get the XFEL, when we get bigger lasers at these facilities, we should be able to do much better diffraction at the highest pressures. And plus our peaks are all very broad because of the natural width of the helium alpha line, which is on the order of 2% bandwidth. And we're hoping to get a kilojoule laser at DCS in Chicago, as well as at the European XFEL in Hamburg, hopefully within the next 5 years or so. So, we should be able to get up to these, maybe even these pressures within the next few years.
Yeah, I'm a neutron scatterer, so I'm sympathetic to having large backgrounds and other instrumentation issues. And if you can improve the data quality through the instrumentation, I think it'll be super exciting to get better quality data under these conditions. Very nice. Thanks.
Yep.
Okay. Any more questions? If not, thank you very much, John, for an excellent talk. And we'll hear about neutrons in 2 weeks from Malcolm. So thank you all for joining us.
Thanks.